morning again, and welcome to the conference. It is my great honor to welcome Professor Peter Wriggers of Leibniz University of Hanover. He is a very well-established researcher in computational mechanics and has significantly advanced finite elements and contact mechanics methods across the scales and different physical domains. He is the editor-in-chief of Computational Mechanics and Computational Particle Mechanics, and he has received the prestigious IICM Gauss-Newton Medal for lifetime contributions. He has authored several seminal tests like computational contact mechanics and nonlinear finite elements, and pioneered innovative multiscale methods, including the recent third medium contact approach and virtual element techniques for nonlinear and multiphysics problems. We are privileged to hear his presentation today, so the floor is yours.
Well, first of all, I'd like to thank the organizers for inviting me here to the beautiful Porto. It's actually my third time that I'm in Porto. The first time I came with a sailboat from England. The second time I was invited to one of the conference, and here I'm again. So I really appreciate to be here, and you will probably also appreciate the city later on. So today I will talk about a field which is a field which I started actually with my PhD thesis. It was on contact mechanics. Then for some years I worked on contact mechanics, and I it was a little bit bored about this topic, so I started to do new things and different things, but then I always sometimes come back to contact mechanics. And this one which I'm talking to you today, the third medium contact, has some specialties, and it's actually a very simple way to enforce contact constraints by using sort of this kind of third medium. And I have extended this in this talk here to multi-field applications in specialty for thermomechanical contact. So first I will give in this lecture some ideas about the third medium contact, and then we will see how it works for the multi-field application. So classically, if you do contact modeling, especially in finite deformations, what you don't have is basically non-matching meshes, which you can see here. You have to do a lot of search things like global search, local search. If you have a sort of two surfaces, and here this is in 3 dimensions, a node to segment contact, you have to do a nonlinear search because this is a hyper surface here, and there is no exact solution or a direct solution for this kind of a point. You have non-matching meshes, and classically what we do is we use mortar methods. It looks like this, which is also not so easy. And actually the contact problem is a non-smooth problem, which means that you need very special algorithms like the augmented Lagrangian schemes and other things more. So you have to do a lot of things for contact mechanics. Nowadays, of course, there are a lot of commercial programs which work, and I don't want to say that you have to do a lot of research in this area, but in the background is quite complex. Now the idea is to go into the third medium. First of all, there you don't need any special contact discretization. You only have to throw in the third medium. You don't need any special algorithms. You just solve your continuum problem. You can the third medium use as a special solid formulation, which you do for a large strain. Based on this, it's actually easy to implement. It's just like a new element with a little bit of twisting, but we will see how it works. And you can include like heat transfer in the multiphysics application. You can do electromechanical couplings. And the thing is that this third medium then can actually even act as a real problem. So let's see what the thing can do. We have here a contact problem, which basically is something like a beam, but inside here is a third medium in orange. The yellow one is sort of the real structure. And now you apply a load here and you push it down. And here is sort of the support of the thing. And what the thing does is this. So you basically squeeze the third medium here together and you get the solution. Now, of course, if you think about it, having these elements and squeeze them together, and actually you can achieve gaps like 10 to the minus 4, 10 to the minus 5, means that these elements are really squeezed together. And still it's working. So that's the amazing thing. And now let's see how we can develop that. So the main idea is to have two solids, and in between you put the third medium. So you just mesh it with a different type of element. The third medium acts then as a barrier. In contact mechanics, we have always 2 or 3 different ways of enforcing the contact. One is penalty method, where you have some penetrations. The other one is Lagrange multiplier method, where you don't have any penetration. And the third one is barrier method, where you basically, when you approach the contact, the barrier gets stiffer and stiffer, and you have basically this control. And here this acts like a barrier method. The thing is, the third medium, of course, should not have any influence on the deformation once there is no contact. It's not close to contact, otherwise you will see a deformation which is non-physical. So this is only, it should only act basically once you have contact. You have to control mesh deformation, because if you squeeze the stuff together like hell, I mean, the mesh does something weird eventually. We will see that. And well, in our case, we also, when we do the multiphysics problem, we have a pressure-dependent heat transfer. We have, and thus this third medium has some physical properties when it, with respect to the heat transfer or the heat conduction. There are some works in this direction. We actually started that like something like 12 years ago. Then we had some work together with Laura De Laurentiis on isogeometric methods here. And then it came up again in the area of optimization. So our colleague from Denmark, Ole Sigmund, with this group, was working in this direction, and they actually pushed it also a little bit forward, which I will see. And then I started also to work again on this topic a little bit. Now let's go with the history. Our first idea was basically to really put the third medium. And then the idea was actually, when these bodies come closer together, we need some sort of a barrier function. And the idea was then to have this medium here like an isotropic medium, like an isotropic embedment. And then once the bodies get closer, to basically make it as an anisotropic medium, which only has a stiffness in normal direction. So the question was how to do that. This is what we came up with. We were computing the Cauchy, the right Cauchy-Green tensor, the eigenvalues, and we took the smallest eigenvalue to compute basically a normal vector. The smallest eigenvalue base was the one which has a squeezing of the elements. And from there we could basically compute basically the structure tensor M, which we put into an anisotropic function here to compute the sort of stiffness relation. And the stiffness relation was something like 1 over the lambda. When this thing gets very small, you see that this term gets very large, and we have a very high stiffness of this anisotropic medium. This was done, and it worked. Here's one example from our old paper. This is sort of the mesh, and this is the result. And you can already see that there's some bulging here, which, well, okay, it's because it's a large strain, but the result is not bad. This is sort of a solution. It's a standard contact problem, no to segment approach, and you see the stress field is quite okay. What you also see is that we did not really get into very small, I mean, that we could not fulfill at that time the gap very well. So we had to do something in this direction. So what were the drawbacks? We always had to do an eigenvalue computation. Okay, can be done, but you have to linearize it because in this, and so it's a little bit nasty. We have severe mesh deformation like here, which sometimes gives trouble if the deformation gets larger. Implementation is complex due to the linearization and things like that, and the approximation of the gap closure is also not optimal in this case. So our next stage was to look at isogeometric formulation, but still we had the same problem here. We had a problem where we did some sliding. You see the mesh deformation is not that big, but anyway, it is also sort of a problem where we also had some drawbacks. And then came the idea to use a simpler function. And this was basically something which people in the Ole Sigmunds group did. They said, why don't we take just the isotropic strain energy function? Forget about this computation of the anisotropic part, which makes a problem. So the anisotropic function, of course, has some requirements. First of all, it should be designed so that there is no influence, as I said before, on the deformation of the third medium when there is no contact. And the other one, the stiffness should be very high value once the bodies get into close to each other, the barrier method. And here you can see what it means. This is sort of a problem which is loaded here and clamped there. So these are two beams. When you load it like this beam down here should not move. So there should be no influence of the third medium on the deformation of this beam. Only if it gets close, and you see here we can even model point contact with this kind of thing, it basically should deform and the stiffness should go very high. The other thing is, you can also see this already here, and we will talk about this, that you have to be a little careful in the design of the third medium, because these elements, if you take standard elements, will deform a little bit differently. So what do we do? We have a strain energy, which we split into a volumetric part and an isochoric part. Simplest choice, near hook material, very, very simple, but with a very small parameter. Instead of taking the standard parameter, the bulk modulus or the shear modulus, you take here something which is much smaller than 1, like 10 to the minus 4. And then due to this term, because this one basically will move the whole strain energy into a point where it's very high for J going to 0, and the pressure also. And you can see this here. Here I have plotted the pressure field. See the J. It's basically for a long time, even for a very small J, nothing happens, and then out of a sudden you have this barrier function. So this one is actually the key to have this kind of formulation. Now, what are the problems if you do this? I mean, you can do this right away, which is very simple. You could implement this even in a standard Abacus thing. But what we get if we don't do anything else, we get self-penetration, we get bulging of elements, and the gap is not closing. So, for example, if I take the same example I saw before, which is this sort of the clamped beam under load, and if you use like standard elements here, triangle element, what you can see here is that they basically overlap, and of course your computation breaks down. So this doesn't work. So you have to do something extra. And this is what we have to define. Now, that means that we have to add to the strain energy function some regularization, which depends on the deformation gradient, which basically controls the mesh deformation. And the idea, this is actually a paper I took from this, a picture which I took from this paper by Fredrickson, was basically to do, say, what we want to have are these first modes, and what we want to suppress are these kind of modes here, the higher order modes which do the bulging. How can you do this? A very simple way is to add a term which is a gradient of f square as a regularization function. Or you do it a little bit more refined, you take something away from that, which also works. Or another thing is to think about the deformation gradient, which is sort of the, you can be split polar decomposition, and f is equal to r times u, and you take the r to control somehow the deformation. This can be done, but always you have to compute the gradient, and to compute the gradient of r, you don't want to do it by hand. Actually, you can do it with HGen, but the code which comes out is a little bit long. So what these people did, they approximated this by a skew-symmetric tensor here and introduced it that way. Now, this is something which you can add, and we looked at this by ourselves, or I looked at it myself, and then I said, okay, in 2D it's very simple, because the R is this one, and if you basically take sort of the formula F equal RU, and you know that U is symmetric, you actually can compute the tangent of this angle just by the components of the deformation gradient. Maybe not many people know it, but if you look it up, it's in my book, actually, non-finite elements. So in this case, it was very neat because I could compute the angle, and instead of R, you can also take the gradient of phi. So instead of having a tensor, you only had this angle, which you could put inside. And actually, what we then also found out, that the angle is not necessary. You can control the tangent of this angle here in this way. So this is very, very neat. It's the simplest way of doing it. And in 3D, then of course, if you want to control the rotation tensor in 3D is complicated to compute. So the idea was here to basically think about the 3D case in a way that you have three directions, and you always take in one direction the rotation tensor. So you decouple in a way the rotations. It doesn't matter because, I mean, you only have to control the stuff. I mean, you don't have to do anything else, so you can couple that and take this skew part of the deformation gradient for the control of the rotation. So this is basically what we have done. The drawback is all these formulations need a quadratic Ansatzfunction because the displacement field, you want to compute the gradient, in a linear function is 0, right? So the other thing is you take triangular elements, quadratic triangular elements, because they are complete, the gradient is constant, also nothing which helps you. So you have to do something else. But now let's first think, if we do this with quadratic elements like Q2 elements, what can we get? And this is the first example, the Q2 elements using the function which we have done. Here is sort of the deformation, large deformations, large problem. Okay, I showed this already. The next, what you can see here, depending on your parameter gamma, and you can see that you get a very nice gap closure. So this, for engineering purposes, 0, right? But this is what you get. And actually you can do then, in a way, a little bit of a study. You can use different parameters in your formula, and you can find out how good you can approximate the gap. But what you also see, the better you approximate the gap, the more iterations you need eventually. Because, I mean, the sort of ill conditioning of the system is a little bit higher, and you need more iterations. But it's all done with the direct solver. Not that it doesn't make any difference on my little computer here. I can run these kind of things in 2 seconds or 4 seconds, so this is not a big problem. But we can approximate the gap. This is another problem which we basically took from the literature, and I made a mistake actually in this one, because the idea here is that you have this box and then you take inside this third medium, but you apply a pressure load in the third medium, basically a suction load. So you basically take all the air out. And I actually made a mistake, because the load parameter, instead of taking 0.1, I took 1. And was astonished that I got a solution, which is this one here. So basically all the air is taken out. You have a full contact here in this part with your computation. So it was working. So I wanted to solve this one, but then I solved this one first. So I was saying, okay, this is quite, let me say, stable, the method, from this point of view. This is also, let me say, a test case where you have this C-box and you get this deformation and the point-one contact, which is quite neat, because this is also this standard contact not so easy problem, but then you can push it even further and apply the load in a higher way, and then out of the point contact you get a line contact here. And you can see that the mesh is very deformed, because this node and this node are connected by one element. So the elements are really extremely not only squeezed but also sheared in this problem, but still working with this regularization. So this is sort of something which is quite neat from this point of view. And then we went further. So we were saying, okay, this is a functional which we have used. And this was a tangent here, and these are the quadratic element, only works with quadratic elements. T2 is questionable. Then the question was, how can we do this for first order elements? And the idea was the following, that we approximated this functional in a way which looks like here. And the idea is basically that you can see here, we introduce a new unknown P1. This unknown P1 basically shall match this form here, which we have up there, and then we compute the gradient of this P1, and by this kind of sort of penalty approach, we are able to approximate the gradient of f in this case, but with the sort of additional cost of an additional unknown, at least for the third medium. So, does it work? We'll see. We have this in the two-dimensional case, and you can also see that we have this in the three-dimensional case here, which was for these different parts of the skew symmetric tensor. These are basically three components. So in the three-dimensional case, we have three additional unknowns, which is a little bit expensive. So the finite element formulation is, I think, straightforward. So you only plug in your classical ansatz functions. This one with the classical form. This is the regularization, and here you basically put in the ansatz functions, you do the differentiation, and there's nothing much to it. This is the result for Q1 elements. You can see gamma is equal to 10 to the minus 5. It's a small value. These are the alphas, alpha 1, and these are, I took 10 to the 4 elements. I could have done less. I mean, it does depend on the element size. But it's interesting that if you take more elements, you still get solutions. You know, sometimes the fewer elements you take, the more, let me say, robust your solution is. But here it still works. So you can see here for this problem we get a nice convergence of the gap. And here is a little bit of a graph, the gap closure versus sort of the, what was it? This is the number of iterations. This is the gap closure versus the gamma. and you can see is the closure is of course for a smaller gamma. You get a here 10 to the minus 7. You get a better gap closure to 10 to the minus 6. This one, or here for 10 to the minus 5. This is for sure fully okay for engineering purposes. And here is the vice versa. So for the sort of largest, the smallest gamma, you of course we take have the maximum number of iterations, and they get less if the gamma is closer. So this 10 to the minus 5 seems to be a good value to do computations in this case. Here was a comparison with classical finite elements, node to segment elements for this problem. And what you can see here, actually, yes, what you can see here, if you have a very small, a larger gamma, you approach the gap being 0, but you are not really correctly getting the sort of contact problem. For a larger gamma, you will sort of approach the gap much better. And this is a node to segment computations, actually with augmented Lagrangian method, which basically gives you the gap closure very well. You can see it here. This is our problem. Here starts the contact. For the small gamma, you get this type of gap behavior here, and this is what you get for node to segment. So node to segment is a lot better, but of course it's a lot more costly. This is basically, it was the same result. So this is basically the C problem, where you can see the node to segment, where you can see the approach by the third medium. And this is another comparison for the whole contact problem here. Node to segment with a fine mesh, node to segment with a coarse mesh, gamma to 10 to the minus 6, gamma, well, we actually checked different ways of improving this contact part, but you can see here that we are very close to the real gap behavior with the node to segment approach, and also with the coarse mesh and the fine mesh. Both match quite well. So from this point of view, I think we are in a good shape with this third medium, so it can be really used for contact problems. And here's a little comparison with running times. So I mean, just to show, I mean, this is all on my machine here. 130,000 unknowns, 100 load steps, solver time is like 35 seconds. So if you have 2,600, this coarse mesh here, you see it's almost real time. So it's less than a second to solve it. So actually it takes more time to do the video than, or to do the plotting than to run the problem. Now, we come to another example which I like very much, because it also shows how the method works. This is two balls or two spheres, and another half sphere or ellipse is moving down to the spheres, so that here is a wall, here it's a wall, and this is open. So what you would expect is basically the following, that this guy here moves down, squeezes this sphere into this corner, and this one here will move out. So when I meshed this and ran it first time, I was thinking, oh, maybe it will work, maybe it will not work, you never know, right? But then I was surprised, because I got this result, which means that really you can actually model with this even something like a thing which moves away. This is non-frictional problem. Here you can see it's squeezed together, here, 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 and this one here is moving out. And it's sort of not rolling away. I mean, if you would run a normal computation with node to segment elements, of course, this would move away. here it's of course fixed by the very small stiffness of the isotropic media which we have here. But the nice thing is you can see how much these bloody elements are, these are triangles before are deformed and still working. And this is actually the stress field, or the pressure, the contact pressure. You can see the contact pressure is here, and there is no contact pressure in there. So that is working correctly. Then we have done the 3D case. This is a C box, which is loaded in such a way that it's moved down, but also moved to the side. So that the idea was to have a sort of contact which looks like this. Actually, this is a contact point. You get a point contact here, because this goes to the side and contacts this part. Here you can see it. So the torsion of the upper element and the lower element. So this was run with linear elements, with this kind of approach here from this point of view. So this can work. And if you look at the third medium, you even can see that the third medium is quite nicely controlled. There is no bulging out a little bit, but in the end it's working fine. And we can even run it further, so then this point contact gets into a line contact here on the surface, and still this is working with the third medium approach. Okay, so from this point of view, this was only deformation and deflection. Now what we want to do is thermomechanical contact. So we have to add the thermal part. First of all, what you do, you split the deformation gradient into an elastic part and thermal part. The thermal part classically is only governed by the volumetric change by the volumetric change related to the temperature. The weak form for the solids, you have the one which is classically given, and then you have the weak form which is governed the thermal heat conduction. In this case, I have only looked at stationary processes. The P, the pressure, the first Euler-Kirchhoff tensor, of course, depends on U and theta, and also the heat flux vector depends on the deformation, as we will see in a moment, for large deformations. So we can use a classical thermoelastic strain energy function for the solid. We have here the coupling part, and here the thermal part. The coupling part is given here, and the Fourier law for related to the initial configuration or reference configuration is given like that in the continuum case. So we have here the influence of the deformation on the gradient. Now this can be put into what we like pseudo-potential form. I always like this pseudo-potential form because I'm working with AceGen, which is a sort of an automatic differentiation tool, and this one gives the fastest code for pseudo-potentials. So it's faster than if you start with the weak form. So that was the only thing. The idea is to put here a potential in there in such a way that you keep some terms constant, and if you then do the classical derivation of this potential, you end up with the weak forms. So that's basically only a trick. So it has nothing to do with new physics, it's just to set it up in such a way that you can basically have here a fast code. So in the variation we have to keep this one constant and this one also constant. Then we plug in our ansatz functions for the deformations and for the temperature, and then we can start our third medium approach. Now for the third medium we have to be a little bit more careful. Of course we want to have the same thing like before, no influence on the deformation and there is no contact, acts as a barrier when we have contact. But then the idea was also to represent in the third medium some thermal behavior like gas or air. Classically, I mean, if you have a contact problem, you have also, let me say, in the surrounding air, if it's thermomechanical one, You have also the heat conduction, which is small. The air heat conduction, of course, is much smaller than the heat conduction in the solids, but it's there, and you can take it into account in this case. So this is what the idea is. And so from this point of view, we have to formulate for the third medium the Fourier law in such a way that we have here the gas conductance, which is multiplied by a term which basically is related to the pressure. So this is also a classic thing. I mean, if you do thermomechanical contact, you have always three parts in the contact area, because due to the roughness of the surface in the contact area, you basically obtain three parts: the spot conductance, where the spots really come into contact, then there is a gas conductance, and the third one would be radiation. So these three things you have to take into account. Here we only took into account a simple form where we have a pressure dependency on the gas constant, which means that this one, when it's squeezed together very much, will get very high values. And so we stop here at the conductivity of the solids. That's sort of the idea here with this kind of law in this case. And then we have to check whether it's working or not. Again, this is of course our simulation which we want to do, and then we can do the same thing as before. We have to add our regularization, and here I only want to use it for sort of first order elements to have a more simpler approach. And the regularization, but has not to be given for the thermal part. It has only to be given for the mechanical part, because the thermal part is just the heat conductance, which does not depend, besides the pressure dependency of the conductivity, on the deformation. So this is basically the same. If you do the derivations, of course you can. I'm always stopping at this form here. I'm sorry about this. I mean, I don't derive the residual and the tangent matrix, because this is all done automatically in my little HGen code. So once I have set up these kind of things, I'm basically done with my coding. But of course, what you have to do, you have to differentiate this with respect to the displacements and the temperatures, and then you get the residual vector. The residual vector has two parts, and then again, if you differentiate that residual vector with respect to u and the tangent, you get a non-symmetric tangent matrix in this case. And what we have done, or what I have done in this code, is not to use a staggered scheme, but to solve the full scheme, the full matrix, which means that I have to solve a non-symmetric equation system. But you can also use a staggered system for the temperature, because in the nonlinear case, the heat flux is depending on the formation, and on the other hand, the constitutive equation for the stress is also depending on the deformation. So you have a coupling in both sides, and from this point of view, for me, it was the easiest thing to run the full scheme with the Newton method. So it's a full derived Newton scheme, and it has also quadratic convergence. Now the first example which you try is of course something like this block, where you apply a temperature and a displacement. This one here is our third medium. This is a mesh for that. These are some of the data. You see the gas constant is 1/1000th of the solid constant in this case. And then due to the displacement, this block will be squeezed down here. So this one will disappear. And then we have to see how the temperature relation is. So for before contact, you can see, I have to say the temperature which I applied at the top was, didn't say this, is 100. And here it's basically 20 or 0, one of both, maybe 20. So there's a difference. If you don't have contact, the stationary heat conduction problem, only the solid has the same temperature because there is no contact yet. So the temperature stays by 100. This is the top temperature, which is now everywhere. And once the contact appears, you get sort of the temperature distribution, which looks like this, which is a classical one. You have here, it was 20 degrees here. So you have 20 here and 100 there, and in between actually it's a linear distribution. So actually I can show you the results here. This is before contact. There you see we have a linear heat distribution in the third medium, which is this thing here. And then it's 100 here. Analytical solution, of course, is only 100 here and nothing there, but this is it. And in the case where the gap is closed and we have the final deformation, we have here the a very small temperature distribution in the third medium, and then we have the linear distribution here. And the analytical one would be a linear distribution from 20 to 100 there. So there's a little bit of a difference here, and the difference is due to the heat. To the pressure dependency of the heat conduction in this case. This is what comes up. So this is one example. Then of course, once you have checked that your method somehow works, you try the next one. The next one was basically the same sort of thing in a way, but two deformable blocks. This one is basically squeezed down. Here sort of we have applied deformation. It's fixed down here, the temperature is 0, and the temperature here is there's a value. So when we try to push it down, the first step, we have here heat conduction in the upper part, which is the temperature, the applied temperature up here. Then here is 0, basically the temperature, and there's a little bit of temperature distribution because of the very small gas constant for the heat conduction. If we get closer, you can see that the heat transfer starts to come up, and if we go to the final deformation, you can see that the heat transfer is sort of across the interface, and what you can also see, it looks quite nice here how the heat conduction works in this case. So this also seems to be okay. And this is the gap closure, which means that the gap here, it's actually, I checked here for the gap closure, it's very, it's closed from the point of view of the engineering solution. Now, of course, we can look at a movie and you can see how this sort of develops and how the gap is closed in this case, and this is basically what we obtain for this part. The next part is, why don't we try the same problem that we tried before, the two spheres. Here this side is sort of closed, this one is open, and we apply as well a temperature as also a displacement. We have this type of mesh, which are linear triangles in this case, and again we obtain the solution, which of course looks like the same solution we had before for the two spheres. But now we have again here, this is the pressure distribution, which also looks the same, and we have also here the heat transfer, which is sort of the conductivity through the interface, and you can also see it's basically here, but you can see also here some sort of little things where, because it's quite close to the other surface, where we have a little bit of a heat transfer. But classically you would say, okay, this is very small compared to that one, so that we have a good solution for this problem. So this is what it does, and I think if I'm lucky I get here also the result. You can see here, which is very small, you have the gas constant, and the heat transfer also goes through the gas. So in the first part, it's there. But once it's squeezed more together, then this disappears here on the left side. And sort of the heat transfer basically goes here. This is sort of the gap function. And then again, when it starts to move, you have a little bit of heat transfer there as well, but then it moves out and the heat transfer goes away and is basically only going through this. So it's a little bit complicated problem, but you can model this problem quite nicely with this third media approach without thinking about complicated contact mechanisms. Now, the other thing is which you could think about is homogenization. If we have a microscale heat conductions, then the asperities might look like this. Then you have a spot conductance and you have the gas conductance in the interface. So classically the heat conduction here depends on the pressure and the temperatures. And I wanted to basically run this type of problem with this third media approach. Here it's Q1 elements, 30k degrees of freedom, again monolithic scheme, 24 steps, and here you can actually see, if you can see it actually, this is one of the load steps where you can see how the residual sort of changes, and you can even see that this is a classical Newton kind of the convergence, like 10 to the minus 7 to 10 to the minus 12, and before it was 10 to the minus 4. So it's a classical Newton approach, and it takes about 7 steps for one load step to converge in this case. Now, how do this look like? This is basically for different stages of the deformation. This is sort of in the beginning. This is the stresses, where you have here the contact contribution, the sigma yy, which is the vertical stresses. You can see that this is basically only the main part is at the spots. If you squeeze it more together, you see then the stress field changes. You get here a different view on this kind of thing, and that means that we can sort of look at the stress field in the contact interface. We can also look at the temperature distribution. This is basically before contact. There's a little bit here, then they come into contact. See the temperature distribution, and when you really squeeze it together, you get this type of temperature distribution, which is almost like linear, but you can also see that it depends a little bit on the roughness of the surface here. I have not, used it further. And then I thought, okay, when I come to this type of conference, I have to show some 3D results. So on Friday, actually, I started to do the 3D case. And some preliminary results. So this is basically a three-dimensional example of 2 blocks. This one block is loaded by this part here, and this is a mesh. So it's 1/4 of this block. So this is the upper block, this is the third medium, this is the lower block, and this is the loading, where the loading is basically the following. We have again a displacement load and also a thermal temperature. So these are some of the values, and you can see here it's an 8x8x4 mesh in this case. This is sort of the undeformed mesh. This is the deformed mesh. Again, we have here a nice contact area. What you also can see is that these were node-to-node, but they are no longer node-to-node due to the large deformation. So again, we have some shearing here in the interface. Also in 3D, it's working fine. And here's the same thing for a 16 by 16 by 8 mesh, which is a little bit larger from this point of view. And we can compare the results. So this is sort of, in a way, a little bit of a convergence study. I took now the third medium off, so now it looks like a real contact problem. The third medium is not plotted; it's there, right? I mean, we could see it here. The third medium is again there, squeezed together, so we get this result. And you can see even for the coarse mesh, it looks quite nice. So the distribution of the temperature over the surface is quite well represented, even for this type of thing where we have node to surface type of mesh. We also get the heat flux in Z direction. It's a little bit disturbed by the fact that here's a high singularity in the solution, so I should have used a different loading, but anyway, so this is what I did in this case. You can see it's working fine here as well, and these are the stress fields which also look quite nice over the surface in this case. So this is what I have done in time, yes, and only to show you the computing times, what you can see here. These are 8 by 8 up to 24 by 24. The number of unknowns is 130,000 to 6,000. Solver time 36 seconds to 1,800, which is a little bit long, but anyway, you can still solve it on this machine. The K and R time, this is the time you need to compute the tangent matrix and the residual. This is linear. And if you reduce the gamma, then you also reduce the number of iterations, and then you get still a good result, but this in shorter times. But anyway, this long solution times also depend on the fact that we have 6 unknowns or 7 unknowns per node. So the three displacements, the temperature, and then these additional fields for the regularization. So I want to stop here and say, okay, what is the third medium approach doing? No contact search, possible to add physical properties to the third medium, which is not so easy in classical contact mechanics. What I have to do still is include friction. There is some work which already did it, but there is still an open part. It can be done. You have seen that the shearing is possible, so the classical way would be to introduce here something like polycrystal plasticity for polycrystals. Can do extension to plasticity, and I'm always concerned with fast codes, so I want actually to compare the efficiency between different regularizations. Either take a Q2 without additional fields versus a Q1 with additional unknowns. In the 2D case, this one works better, so it's faster. So there it's clear, but in the 3D case, I don't know. I have not coded this one, so I cannot tell you. But this is maybe next week anyway. So with this, I'd like to close, and thank you very much for your attention. I hope I showed you a little bit of a new sort of topic, and there's a lot of things to do. Maybe some of you want to go ahead and do some work in this direction. And here's some sort of papers which you can look at to see how the method works. Thank you very much.
Thank you very much for a very interesting and insightful presentation. I think we have time for a couple of questions. I don't know if anyone wants to raise a question. So I can start. So one of the things that impressed me was the strategy that you used coupled with homogenization. But I couldn't really understand what do you do with the third medium if you want to homogenize the relations that you use in terms of stresses, and so there is a stiffness associated with the third medium, I guess. So how do you homogenize that, or you ignore it?
Well, I think in this case I want to ignore it, right? I mean, you mean the homogenization for the thermal contract,
That's right.
Yeah. First of all, it has to be done 3D.
Okay.
to be frank. I mean, this was just something to show that it's worked, because, I mean, all these asperities and stuff like this is a 3D thing, right, in reality, on the micro scale. So this is one thing one has to be very careful about. But the other thing is that I think the third medium here is acts only as sort of a property. So you get the gas conductivity with the third medium, which is automatic. And if you get closer and closer, you get the gas, the spot conductance, which is the conductance of the solids. So actually you can monitor what people thought about this with very complex models. I mean, you can find some analytical models about this in the literature, very old ones. We have worked with Giorgio Savarese on this topic some years ago, but this can be done. But here it's automatic. So let me say, the stiffness of the body is only for the barrier function. In the thermomechanics, you have to put the sort of the real value of the gas inside. Okay, so I don't know what to do with the radiation, but in the old days we found out radiation is sort of a minor factor for this kind of problem.
Thank you, Peter. Very interesting. In the particle funnel element method, we also have a sort of a contact domain between bodies, and this is automatically detected at the mesh generation level, meaning that you don't need to mesh the whole domain. You could using kind of the Delaunay, you could identify your contact region. This will reduce the domain that you have to. The third domain will be reduced to the actual. Would that be possible, particularly for metal forming application? That was the object of interest. I think Professor Oliver and his group.
I know.
So basically the question is you could reduce your third domain by I would say a more adaptive strategy using mesh generation.
Yeah, I have seen, of course, this. The only thing is, I mean, okay, you can do it, and nowadays, I mean, you still have to do a search.
Yeah.
And here you don't have to do any search, but you could apply this methodology also to the one which Olivier has done. I think that he has 2 papers on that. I know them. Yeah.
Okay, this is the advantage. You don't need to do the search. Yes.
The third medium has an additional degree of freedom for the regularization. So comparing with the classical contact algorithm using the Lagrange multiplier, how is it fast? Like if it's too big, then there will be a lot of DOFs inside because of the third medium.
Well, I mean, here what we have is a barrier method. In a way, right? I mean, in contact mechanics, you have this barrier method as well, which is like the reverse of the penalty method, which you can take. You don't have a Lagrange multiplier here, right? And the regularization parameter is something different. Has nothing to do with. It looks a little bit like an, let me say, augmented Lagrangian type of technique, but it has nothing to do with that. It's only for the control of the shape of the element.
Fully understand the equations for the third media, but I got probably a naive question here. For the third media, do you have to use Lagrangian mesh to capture the formulation of the third media, or are you okay to use Lagrangian mesh, which you naturally don't have the?
Well, I mean, I think you can do any mesh you want, but in this case it was Lagrangian mesh, because we have used an isotropic strain energy function based on the sort of Lagrangian formulation.
You want to make sure the contact, the direction is captured.
Yeah. But maybe you can also use a different, an updated Lagrangian type of meshing if you want, right? But I have not done that.
But that's the main reason to use this Lagrangian mesh, to capture the direction correctly.
Yeah.
I have a question. So I saw the large deformation in the third media area. So in your case, it works well for the steady simulation. But I'm interested with the dynamic simulation, because for the large deformed mesh, when we do the dynamic simulation, the high frequency issue maybe that will be a difficulty for the dynamic simulation, the robustness of time duration.
I have not checked it actually. I mean, we have not tried it. I mean, something somebody could try. So this is a point of new research to see how good it works in this case.
Okay, thank you.
But I have the feeling that it should be working somehow.
Yeah, at least for the static case it works very well.
Yeah, but my feeling is also dynamic should work. But I have not tried it. Maybe next time.
Just one final question. Could you elaborate a little bit on the challenges that you'll face by modeling friction through the third medium? Because you'll have to introduce that on the constitutive behavior of the third medium, isn't it?
Yes.
So how do you see that going?
Well, okay. What I would do is, first of all, there are two things which you have to do. The first one is you have to somehow compute the normals and the tangents in a way on the surface, which can be done. But it needs some sort of a search algorithm. But can be introduced because you can compute the normals for the whole surface anyway. And then the other thing is what you have to do, to my face, is, I mean, you know crystal plasticity, and you have the slip planes. So if you put this kind of model inside with the slip plane, only one, you should be able to recover friction. That would be my approach at the moment.
Okay, let's thank Professor Peter Wriggers again.